All right. 8-1, day 2. Again, this one is mislabeled. We are doing dilation. All right. Today's day 2 of dilation. So we're going to cover two things today. First, we are going to describe a dilation. All right. So we have got triangle ABC prime. Okay, ABC prime is the image, okay, and triangle ABC okay, this is your pre-image, so this is where you started, and that's where you ended, all right, after a dilation. We're going to describe the dilation, then write the coordinate rule, okay, coordinate rule, to represent it. Okay, the coordinate rule. So we're going to end by writing the coordinate rule. We're going to do a couple things before we get there. Okay? So, remember A, B, C, you can tell this is your pre-image because there are no prime tick marks. And this is your image where it ended up because there are prime tick marks. So this is, I like to say, the final resting place of your ABC triangle. So we went from a smaller image to a larger image. So this is an enlargement, all right? And so let's see. First step, step 1, identify two corresponding sides and their endpoints. So it gave us corresponding sides AB, and AB prime, okay, are corresponding sides. So the endpoints of AB are, all right, so let's put in our endpoints. Well, A is, remember, this is our origin right here, all right, it has slid, it is not in the middle as we normally see it, so it's slid right here. So we do need to take that into account. So for A, we're at -3, 0, and B is 0, 2. Now A prime is here, is -9, 0, and B prime is 0, 6. All right, we've identified our corresponding sides and their endpoints. So what are we going to do with that? Well, if you'll notice here, we have that ever-beloved distance formula that we all love to hate. Okay, so we're going to use that, and we're going to find the lengths of these corresponding sides. And we're using the distance formula because there were no sides that coincided with the background graph itself. If your sides coincide with the background graph itself, you can just, count up the blocks. But we don't have that option here. All of these are at a slant. So we are going to find the distance from AB and then find the distance from A prime to B prime using our distance formula, which we love to hate it, so we need practice with it anyway. So first we're going to find the distance of side AB. All right, and it's the square root of, all right, our x2 is 0, minus our x1, well, that's -3, the whole thing is squared, plus the difference in your y's, okay, y2 is 2, minus y1, which is 0, and that whole thing is squared, all right? So a negative times a negative is a positive, 0 plus 3 is 3, 3 squared is 9. All right, 2 minus 0 is 2, 2 squared is 4, and you end up with the side of AB being the square root of 13. We're going to leave it just like this momentarily because we aren't done with it, so we don't want to really do anything with it quite yet. So we're going to leave it as the square root of 13 for now. So we have found the length of side AB. Now let's find the length of side AB prime. All right, so we're going to find the length of side AB prime. Again, our distance formula, which everyone loves to hate. So first up, our difference in our x's. So that is 0 minus a negative 9. That whole thing's squared. Plus the difference in our y's. So y2 is 6 minus 0 squared. Okay. So again, a negative times a negative is a positive. 0 plus 9 is 9. 9 squared is 81. 6 minus 0 is 6. 6 squared is 36. And so a prime b prime is the square root of 117. We're going to leave that one alone for right now as well. So we have found the lengths of our corresponding sides. Now, since we have our lengths of our corresponding sides, all right, we can calculate our scale factor. Now, if these had been straight up and we were able to just count, all right, the blocks for the length of our side, we could skip this whole step and simply go here. All right, so we're going to find the scale factor. We're going to find the ratio of AB, all right, AB prime is square root of 117 to AB, which is the square root of 13. All right, and we're finding K, because that's our scale factor. Now, we have the square root over a square root, so we're going to do the square root of, we're going to make a bigger square root because it's both in our numerator and our denominator. And we're going to go 117 over 13. Square root of, and if you do 117 divided by 13, that's actually 9. Now we've gotten to the square root of a number we actually know. The square root of 9 is 3. So K is 3. All right. So we have a K of 3. Cool. So now we know that we are dilated by a 300%. So this triangle is 300% more than this triangle. And we know 3 should be a whole number because our original got much larger when it dilated. Now, yesterday, we were given the coordinates for the center of dilation. Instead, we're actually going to work backwards and find it. Because remember, in math, we like to work backwards a lot to help solidify that knowledge that we've already learned. All right, so we're going to find the coordinates of the center of dilation. So we're going to find our AB. Okay, we're going to find out what we were dilated with. So we are going to find the AB. All right, and remember when we are using this big formula that we learned yesterday, that what we're doing is we are taking whatever we dilate, the center of dilation, moving it to origin, and then moving it back to where it belongs. So that is the minus A minus B, and then plus A plus B. All right, so it says to find the center of dilation AB, use the scale factor 3, that's what we found, and the coordinates of the corresponding vertices A and A prime to find the values of A and B. Okay, now the values of A and B, remember, is moving to origin and moving back to its original location. So we're using A and A prime, and we have those locations right here. Okay, on this side, it's going to be to A prime, because that is what we dilated to. So we are going to have A prime over here, which is negative 9, 0. Okay. And then we have K, which is 3. Now on this side of the equation, we are actually going to use A, because this is our starting point. So this side is taking your starting point, moving it to the origin, moving it back, and getting your dilated point. Okay, so we're going to deal with our x first. Okay, this is our x side. So our x is minus 3, Then we have minus a plus a. All right, that's all of my x. Then we have our b. So again, my scale factor is 3. My y in this case is 0 minus b plus b. All right, and this is my y. All right, this is my y. So let's separate these out. We're going to separate these out into two groups. We're going to separate out what goes with x into one equation, and we're going to separate what goes in y to one equation so we can find the x and the y. All right, so we're going to do our x's first, and then we'll do our y's. So we are going to do minus 9 equals 3 times minus 3 minus a plus a. All right, this is all to find our x, okay, or a. All right, so let's see. First thing, we're going to distribute. So minus 9 equals minus 9 minus 3a plus a. Then in class, we talked about combining our like terms. So that's minus 2a. Because remember, if you owe 3a's and you pay 1a back, you're now at negative 2a that you owe. Next step they wanted me to do in class was add 9. All right, so 0 equals negative 2a. Last step we did was divide, and so a is 0. So our a is 0. Okay. Now let's find our x. So for this, we're going to find our y. We've got 0 equals 3 times 0 minus b plus b. Okay, so we're going to distribute. We got 0 equals 0 minus 3b plus b. Combine those like terms on the same side. Okay. Oh, that's 0. 2b. We're going to subtract 0. Someone in class, one of my classes said add 0. It's the same whether you subtract or add. And again, last step, we will divide, and b also equals 0. All right, so we have found our center of dilation is 0, 0. That's our origin, okay? We were dilated. The center of our dilation was about our origin. All right, and we just mathematically prove that. That's really all we've done. So describe our dilation. So when we describe a dilation, all right, so first we found our k, which is 3, scale factor. All right, we found our center of dilation. Okay, and that was our origin of 0, 0. Now finally, back up here, it said we were going to write the coordinate rule, and here's all that means, okay? So you take the xy, and what's going to be happening with this xy? Well, since we have our 0, 0 center of dilation, and our scale factor is k, we actually don't need this very long equation for dilation. We can use the simpler one, where we just take our scale factor, multiply it by x, and we take our scale factor, multiply it by y. And we do this to every xy of all of the points to make our dilation. Okay? So when it asks you to do a coordinate rule, this is what it's talking about. What rule is the coordinate following? When we do whatever it is we're doing to it. This time we happen to be dilating. All right, so that's the first thing we're talking about, is describing dilation, because yesterday we did this forward, now we've done it backwards. All right, now let's move on just a little bit. Okay, on the back we're going to use dilation in composition. Composition simply means we are doing more than one transformation to a shape. Dilation just happens to be one of the moves we are transforming this shape into. So we did an entire unit on transformation a while ago. It was several units ago. So let's review our transformation rules, because today we're going to use rotation of 90 degrees. Well, there are other rules besides that, and we want to make sure we have those in our notes this time so we can go back and use them whenever we are asked to dilate in composition, because what it's going to ask us to do with dilation is going to change. So we want to make sure we have them all. So translation. Okay, so first translation. Now remember, translation was a slide. Translation just means you are sliding your entire shape, right, left, up, down. We are translating it. So what happens, we're going to write our coordinate rule. What happens to our original xy? Well, you add your A, and then you add your B. That looks very similar to what we were just doing with this. All right. So what we added here was scale factor and then moving it back from origin. So all of this, remember, is tied together. All of these rules end up tied together. So that's our translation. Then we learned about reflection. Reflection, remember, is that mirror image. And we reflect over two main lines. Now, we reflect over other things, but we have our two rules reflect over two main lines, and that is our x-axis, and then our y-axis. Now, and when we reflect over other lines, that is when we get into moving things to origin and then moving them back. So we've done that as well. So, but here's our starter rules. When we do a basic reflect over our x-axis, okay, what is our coordinate rule? Well, you take your original points and you change your sign in front of the y. All right. We also reflect over the y-axis. And when we reflect over the y-axis, our coordinate rule is you change the front sign in front of the x, okay, to get it to reflect across the y-axis. Now, if you've read ahead, you know that it is asking us to rotate 90 degrees clockwise. All right, but if you think back, when we learned our rotation rules, okay, our rotation rules were given to us counterclockwise. And we're about to review why. Okay, so counterclockwise from about the origin. Counterclockwise spins to the left. All right, and here's why. This is, all right, quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. All right, so if we have a shape like we do here, entering quadrant 1, our rules are going to rotate counterclockwise as they are given. So a 90-degree counterclockwise rotation ends up in quadrant 2. 180 degrees ends up in quadrant 3. And 270 ends up in quadrant 4. All right, and we have different rules for 90, 180, and 270 spinning counterclockwise. This is asking us to rotate 90 degrees clockwise. So if we are rotating clockwise, what rule are we actually following? Well, we're actually following the 270 counterclockwise rule. All right, and you'll see that. So here's our coordinate rule, and as we review our rotation rules going counterclockwise, you'll see that rule pop up. But it won't pop up for the 90, it's going to pop up for our 270 rule. So let's get down our coordinate rules. So when we rotate 90 degrees, our rule is we're going to flip those numbers, all right? So your y is going to be in your x location, and your original x is going to go in your y location. You're going to change the sign in front of that first number, okay? So y not only is going to be written first, it's going to become your new x, you're going to change your sign. Because remember, these negatives just mean we're changing our sign and not that the number is actually negative. Okay. Then when we rotate 180, this is the one that doesn't matter if you rotate counterclockwise or clockwise, you always end up in quadrant 3 or 2 quadrants away from where you started from. Okay? So we start with our original point, and what happens is we are just going to change the sign in front of both our x and our y. And then finally, our final rule we learned multiple units ago was rotating counterclockwise about the origin 270. Okay, our coordinate rule for that is xy. And our y will get written first as your x. And then you're going to change that sign in front of your original x and you write it second. And that is the rule it has you follow when you go 90 degrees clockwise, is your 270 counterclockwise rule. All right. And then finally, we have talked about dilation yesterday and today, and we had a basic dilation rule when all you have is a scale factor and you're dilating about our origin. All right. So we have our original points. Here's our coordinate rule. You take your scale factor and you multiply it by your xy, and remember, if it's an enlargement, your scale factor has to be a whole number, and if it's a reduction, your scale factor must be a fraction to get them the appropriate size. So let's see what we're doing today. So dilation in composition. So we have a rectangle, WXYZ rectangle with these vertices. Graphed it for us. And what's it want us to do? It wants us to graph this rectangle and its image. Okay, after a rotation of 90 degrees clockwise, all right, about the origin. And so then we're going to take this image and we're going to then dilate it center around the origin with a scale factor of 1/3. So we're going to do an enlargement or a reduction. Well, it's a fraction, so we're going to do a reduction. So first we're going to rotate this shape. And then we're going to take that rotated shape and we're going to dilate it and get it smaller about the origin. Okay? So that is what it means by composition. It means you take your shape and you make 2 moves. All right? So, but that second move is based on the secondary shape you have. So let's see what that is in practice. Okay? So step 1, graph the rectangle. They did that for us. Go us. We don't have to do that. So we are going to rotate 90 degrees. Now remember, we rotate 90 degrees clockwise about our origin. We are following the 270 counterclockwise rules. So we are going to flip our numbers and we're going to change the sign in front of our original x. So W prime would then be 6, -3. X prime is 6, -9. Y prime is 3, -9. And Z is 3, -3. Now we're going to graph this secondary prime shape. So W prime is 6, -3. We're going to label it prime. You know it's a secondary shape because it's a tick mark, so this is W prime. X prime is 6, -9. Okay, X prime, label that. And then 3, -9. Okay, right here in the middle, label that. And then 3, -3. Right there in the middle, Z prime. All right, we're going to connect our dots. Now, when you rotate, please make notes. The orientation of our shape rotates. So when you rotate, your shape is no longer a horizontal rectangle, it is a vertical rectangle. We rotate the whole shape, all right? We rotated from here to there, 90 degrees. All right, so we have our secondary shape. Now, after you have your secondary shape, you are going to take this image, okay, graph the image, okay, of this rectangle, our prime rectangle, after a dilation centered about the origin with a scale factor of 1/3. Okay, so we know basic dilation, you take your x, multiply it by your scale factor, take your y, multiply it by your scale factor. So we are going to take our prime coordinates. So 6 minus 3, 6 minus 9, 3 minus 9, and 3 minus 3. Take our prime coordinates, and now we're going to take this shape and dilate it. Okay, so 1/3, because k is 1/3, 1/3 of 6 is 2. 1/3 of -3, -1. 1/3 of 6 is 2. 1/3 of -9 is -3. 1/3 of 3 is 1, and 1/3 of -9 is -3. 1/3 of 3 is 1, and 1/3 of -3 is -1. Okay? Scale factor, time each of your x's, and times each of your y's of your secondary shape. Now you notice these have 2 tick marks. These are double prime. Okay? So let's graph our w double prime. So 2, -1. W double prime. 2, -3 is x double prime. 1, -3, y double prime. And 1, -1 is z double prime. All right, our rectangle just got much smaller. Okay, it is 1/3 of the size of this rectangle. But when we dilated, please make note that the orientation of our rectangle did not change. All it did was get smaller. Okay, now take this one step at a time. And these do take a hot minute to do. All right, so give it the time it deserves. And if you need to, definitely use your day 1 notes to refresh your memory. All right, good luck.